This podcast is brought to you by LMU Munich.
This talk is about self-reference, something Hannes and I worked on and spent some time on. And I mean, just to give you a rough picture what this is about, there are many self-referential sentences that are studied in logic. The most famous self-referential sentence in logic, I suppose, is the liar sentence. So something of the form, the sentence I'm uttering right now is not true, or I could write it on a whiteboard. So the sentence on this whiteboard is not true. This is a typical self-referential sentence because it's making a claim about itself. And these sentences are of great interest, I mean, just in themselves, but these sentences have also been used in the theory of truth extensively. So there are certain limitations that are imposed on truth theories by the paradoxes that arise from these self-referential sentences. Hannes and I have a strong interest in applications of these self-referential sentences also to other predicates, such as necessity or analyticity or knowability. And there are many consequences that can be drawn from them. In mathematical logic, self-referential sentences play an important role in Gödel's incompleteness theorems, in particular the sentence that claims about itself that it's not provable. And there's also, mentioning this because of Hannes, the theory of semantic dependence. Somehow, when you try to evaluate the sentence or a sentence that makes a claim about itself, it seems somehow that the sentence depends on itself. And self-reference is one particular example where you seem to have a loop. And that's also why this is an interesting topic. And after working for 25 years and using self-referential sentences for 25 years, I've now come to the conclusion I still don't understand what self-reference is. So I thought I'd give a talk, perhaps without a very clear conclusion. And but I think there are also some problems that can be found in the literature. So I think it's not only me who is confused about some features. The main focus will be on formal languages, but I will go back and forth between formal languages and natural language because the constructions they are very parallel, and sometimes examples are more easily explained in natural language. But my main interest is, of course, in applications to formal languages. So what's going on with certain self-referential sentences in formal languages, Gödel sentences, Henkin sentences, truth tellers, and so on. Then before starting really with the material, I should say, I mean, I've collected some results from the literature, but I've learned a lot from email exchanges with Albert Visser. And so many of the results, observations you're going to see have been first made by Albert. And I mean, these emails have helped me a lot. Okay, so the question will be, what does it mean to say that a certain sentence says of itself that it is P, where P is some predicate, one-place predicate. So for instance, what does it say that a sentence says of itself that it's true, that it's not true, that it's provable, and so on. And now there seems to be at least two problems in this. Well, first, there is about itself, that's the problem of self-reference, but there's also the problem about saying about something. And some philosophers, Hermann Kapellen for instance, have worked on saying about. And it seems to be a fairly vague notion, and it's unclear what saying about, how that is going to be reconstructed. But we are dealing with these, with both of these problems of saying about and self-reference. But saying about, I mean, that's not my objective to analyze this phrase in this talk. Okay, so when I talk about self-referential sentences, I should emphasize I'm not only talking about the problematic sentences like the liar sentence. Actually, since I will concentrate on mathematical languages, the liar sentence won't play a major role simply because truth isn't definable in those languages. So for a change, I'm not going to talk about the liar. But there are also very simple predicates that can be used in that construction. For instance, there is a sentence that says about itself that it's identical to itself. That's completely unproblematic, but it's still a self-referential sentence. And we'll see even these cases are not completely unproblematic. There are also other, fairly straightforward syntactical properties. A sentence could say about itself that it contains a certain symbol, a certain letter, for instance. But of course, the interesting predicates P are those like provability, truth, and so on. So in particular, the Gödel sentence says about itself that it's not provable. Then in the 1950s, Leon Henkin asked, okay, there's a lot to be said about the sentence that says of itself that it's not provable. What about the sentence that says about itself that it is provable? And this is known as the Henkin sentence. Then we have the liar sentence that says about itself that it's not true. Corresponding, we have the non-negated predicate is true. So what about the sentence that says about itself that it is true? I said I won't deal with the unrestricted truth predicate, but even in mathematical languages, you can construct partial truth predicates, and they can be expressed. So you can get truth tellers even in formal languages like the language of arithmetic. Okay. Then when we deal with such sentences in a formal framework, I think there are two dimensions of intentionality hidden there. The first one is, which is very well known, is when we are talking informally about the sentence is provable or is not provable, we have the problem of how to express provability in the formal language. And there are different ways to do so. And that has been studied very extensively by Pfefferman in the 1960s and others. And this is, I guess, fairly well understood, even though there are still some deep problems there. But there is a second dimension of intentionality when we deal with these sentences. Namely, how do we express self-referentiality? Normally, we just say, well, use the usual Gödel construction and you get self-referential sentences. And in some cases, it doesn't really matter how we get these allegedly self-referential sentences. But in some cases, there are choices to be made, and the choice could impinge on the answer to the formal question. So for instance, about the status of a Henkin sentence that says about itself that it's provable. It's not only the choice of the provability predicate, it's also the choice of how we achieve self-referentiality. And I will then try to discuss the effects of imposing certain restrictions on how we get self-referential sentences. Okay, so the first I have to make some definitions. Sorry about that. I will need a theory wherein we can talk about syntax. I don't have to be very precise here. You can take some arithmetical theory, because I always get teased by my colleague Gabriel Utzquiano, because I always start talks by, well, let sigma be any theory. Next sentence will be, for instance, piano arithmetic. It's never anything else. So for a change, I go for a slightly weaker theory, I sigma 1. Don't worry what that is. I mean, I could use also set theory. I could use a direct axiomatization of syntax theory. Wouldn't make a big difference. The only restriction I have to make is I would like to have a language where I have for any expression E, the quotation for E. In an arithmetical framework, we can't talk directly about sentences and expressions, but I mean, list all the expressions in some alphabetical order and number them, and then an arithmetical theory can talk about expression via these coding in the natural numbers. And then I would like to have a symbol for this number in the language, and this will be denoted by E in these corners. Then when one studies the Gödel incompleteness theorem, very often people talk about fixed points. So they say, let the sentence so-and-so, f of phi, be a fixed point of the predicate phi. Think of this sentence f of phi as the sentence that says about itself that it has property phi. So I have defined here a more general notion, the notion of a fixed point operator. This is a function that takes a predicate, such as is provable, is true, is self-identical, whatever, and returns a sentence that satisfies this equivalence. So the sentence f of phi is equivalent to phi of this sentence. And I will give you some examples later on the next slide. So that's here, that's the Gödel sentence. So in the language of arithmetic, we can define a provability predicate. So this predicate BEW for beweisbar, V says, well, V is provable. I mean, just take that for granted that this can be defined. This is what Gödel showed for a certain specific sigma. And then the fixed point operator, if you apply that to this predicate, it gives you a formula, call it gamma, such that you can prove in sigma, gamma is equivalent to not provable gamma. And this gamma is then called a fixed point of this predicate, not provable. And what Gödel showed is you can define such a fixed point operator, because in the formal languages, of course, we don't have the tools for defining self-referential sentences as in natural language. So we don't have demonstratives, we don't have indexicals that you can use to say, this sentence I'm uttering right now is not provable. But there is a fairly well-known trick. So if you should have studied the Gödel incompleteness theorems, I'm not going to go through this, just to remind you what you need in the formal language is a function that allows you to replace some variable with the name of a formula. Once you have got that, then you can basically get this effect that allows you to construct sentences that somehow say about themselves that they're not provable or whatever. But I mean, I will refer to this as the standard Gödel construction, but I won't go through the details here. But very often, just having this, so a sentence gamma that is equivalent to the predicate and then with the sentence or the name of the sentence inserted into that predicate, that's a fixed point, that suffices for proving many theorems about these sentences. In particular, once you have got this, you can prove Gödel's first incompleteness theorem, and how you actually get this gamma is not really important. The main thing is it satisfies this condition, and then you can just go on. How you got this, in particular which fixed point operator you have used in order to get gamma, doesn't matter. And I mean, it's not hard to show that there are actually many different fixed point operators. The Gödel one is just one very specific fixed point operator that allows you to get fixed points for any predicates in a fairly mechanical point. But in fact, for any given predicate, the set of fixed points is actually fairly complicated. So if I'm right, for any given predicate in arithmetic, the set of its fixed points can never be arithmetically definable. That's a slight extension of the Tarski's theorem on the undefinability of truth. So I don't know whether somebody has really studied these sets of fixed points for a given predicate. And I would be grateful if you could let me know if you're aware of anything in this direction. So there are many different fixed point operators, and the question is which one is the correct one, for which should we actually say that gamma says of itself that it's not provable? Is it sufficient if it just satisfies this condition here, or do we expect more? I mean, I suppose, and we'll see examples where you actually would like to have a sentence that satisfies more conditions. Okay, I should say that even for this Gödel construction, some authors such as Peter Milne and Richard Heck have questioned whether such a sentence obtained in the standard Gödel way really says about itself that it's not provable. Even that doesn't seem to be clear, but I'm actually quite happy with the Gödel construction. Okay, so now we go back in history, and I think the first time where the different fixed point operators and ways of achieving self-reference came into focus in mathematical logic was when Henkin asked his famous question in the Journal of Symbolic Logic. So he started with a theory sigma, standard formal system for arithmetic. Never mind what that is, take piano arithmetic, take I sigma 1, doesn't matter. And then we can construct a sentence which expresses the proposition that the formula with the Gödel number Q is provable in sigma. So in a sense, this sentence says about itself that it's provable. I mean, nowadays usually people say, what about the sentence that claims about itself that it's provable? Is this sentence provable or not? I mean, it's very similar to the truth teller sentence, and people were first a little bit puzzled whether that question can be answered. And this is the first time, I think, where the intentionality of self-reference played an important role. Okay, I should say, if you just insist that the sentence is a fixed point of provability, then there are straightforward answers. For instance, one could have said, I mean, if it's just about a sentence that is equivalent to the claim that this sentence is provable, take a tautology or take something like naught equals naught. That's surely provable. It's provable that it's provable, so it's a fixed point, but that's not really an answer to the Henkin problem. So there are fixed points which are not self-referential. The sentence naught equals naught doesn't really say about itself in an intuitive sense that it is provable. And I think there's also something like that must be implicit in this question when Henkin said, well, this must have, the sentence must have Q as its Gödel number, and then the sentence must say about Q that it's provable. Okay, when people try to answer Henkin's problem, in particular Kreisel tried to answer this problem, he had to make two aspects more precise. First, and I mentioned this already, he had to fix a provability predicate. So there are different formulae expressing provability in arithmetic, and basically what Kreisel said is a formula expresses provability in sigma if it proves that the sentence is provable if the sentence is provable. So this is known as weak representability, and there are many different predicates that represent provability in arithmetic. But that was Kreisel's answer. It's still kind of the best general answer there is, but there's this intentionality that you can express this notion of provability in sigma in different ways. Then the second problem, which is more relevant for this talk, is there's also this intentionality of self-reference. So once you have fixed the formula that expresses provability, we are here interested in provability for Henkin, for the Henkin sentence, when does a formula express about itself that it has this property? So I just said naught equals naught won't do the trick. That's not an answer. A formula that says about itself that it has a certain property must satisfy certain additional conditions. So, and I take it that this is basically Kreisel's, maybe already Henkin's restriction on what it means for a sentence to be self-referential. They are not really very explicit about that, but Kreisel emphasizes that his example he gives satisfies these conditions, and Henkin seems to be happy with that in the review of Kreisel. So the sentence that says about itself that it is provable, or here I just have used P, so I try to be more general. The sentence must be of the form PT, where P is the predicate expressing, say, provability in our case, and we must have a term T, and this term must then provably denote itself. That's the condition for self-referentiality. That's like saying it must be of the form, this sentence is true. Then you have a term in this sentence, namely this sentence, the sentence I'm uttering right now, and that denotes the sentence itself. That's a condition. Otherwise, the sentence is not self-referential. And that means, for instance, trivial fixed points, such as not equals not, are excluded as self-referential sentences. So they are not an answer to Hankin's question. And now what you need is some sentence that satisfies this condition, so that says about itself, and where P is a predicate weakly representing provability in arithmetic. Okay, here's a side remark. One problem is, if you define self-referentiality in this way, you can't have self-reference in a language such as piano arithmetic. Simply because T will be of the form, if you do it in the Gödel way, must be a fairly complicated sentence, talking about substitution of a numeral, blah, 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 and you don't have such complicated terms in the standard language of piano arithmetic, where you just have plus, times. There you would have to re-express this term using predicates. So strictly speaking, if you haven't got function symbols for these complicated functions, you can't have self-reference in piano arithmetic, which is already a little bit strange, but I think this is behind the discussion between Heck, Peter Milne, and so on, who claim actually in the Gödel sentence you do not really have proper self-reference. Okay, I find this odd, but let's forget about this. Let's assume we have got function symbols and we have these complicated terms in our formal language. Okay, now I will show you Kreisel's answer to Hankin's problem. So Kreisel's answer to Hankin's problem was, so we are considering the sentence that says about itself that it's provable. And Kreisel replied, actually, it doesn't make sense to talk about the sentence that claims about itself that it's provable, depending on how you express provability and depending on how you express self-reference. You can construct a sentence that somehow says about itself that it's provable, where the sentence itself is provable. But then if you re-express provability in a slightly different way, and also self-reference is a little bit tricky, then you can also construct a sentence that claims about itself that it's provable, but this sentence is now refutable in sigma. So there's no definitive answer, it just depends on how you express that in the formal language. So maybe we go more detail through this in some detail. So first he said, here's the first answer, the first construction, where we have a provable Hankin sentence. We have a formula that expresses provability in the sense of weakly representing provability, and we have a term T1. Well, this is a provability predicate, and this second clause here means that provable T1 is a self-referential sentence, because it says about T1 that it's provable, but T1 denotes the sentence. So it satisfies Kreisel's condition for self-reference, and in fact the sentence is provable. Now here this is exactly parallel, except that we have a different provability predicate, and we have a different term, but they satisfy the same conditions, but this time we have a refutable sentence. Okay, so, sorry, now this is really the worst page, and will become better again. But it's so interesting because I mean, there's usually a story that is told about Kreisel's answer to Hankin. And the story is that actually what Kreisel did is he defined some very weird provability predicates, and depending on which provability predicate you pick, you can get a refutable sentence or you can get a provable sentence. And that seems to be generally assumed. But actually, there is something more sinister going on. And I mean, it seems to have escaped everybody, except for Albert, of course. But even Albert wasn't aware of that. I mean, just when he went back, prompted by me, so that's my contribution. I prompted Albert to think, and with good results. Yeah, and something weird is going on. Okay, let's just. I mean, this is what's going on formally. I will then give a more intuitive example, but here for those who are interested in these formal details. So first, we fix a predicate for provability. Actually, it doesn't matter which one you choose. This could be the standard provability predicate, the one you find in Gödel's paper. Okay, then you apply the Gödel diagonal lemma, and you get a term T1. This is a substitution function, very complicated, doesn't matter. That denotes this sentence, T1 equals T1, or T1 is provable in the standard sense. Okay, this is an application of diagonalization, but this doesn't guarantee self-reference. But now we introduce the provability predicate that will then give the Henkian sentence that is provable. And this is the provability predicate. A little bit strange. It says x equals T1, or x is provable in the standard sense. And now what's really strange is now you would expect, I mean, if we did it in the standard way, we have a provability predicate. Now we apply diagonalization and get a sentence that says about itself that it's provable in the sense. But no, that's not the way it works. Because we have picked T1 in a certain way, this is satisfied. This is the Kreisel-Henkin condition for self-reference. And then, of course, if you plug in T1 in this formula, you get a provable sentence simply because T1 equals T1. Hasn't got anything to do with provability. And we get a provable sentence. I mean, what I haven't proved here on this slide is you still need to show that this formula weakly represents provability. But that's not hard. I mean, it's provability except on T1. It could differ on T1. But since T1 is provable, and this is provable, it's trivially weakly representing provability. So something weird is going on because you first apply the Gödel diagonal lemma, and from this you define the provability predicate instead of doing it the other way around. I won't go through the second part of Kreisel's observation, but if you start with a term T2 that is identical to T2 is different from T2 and T2 is provable, and then it go through the same reasoning, you get a refutable Henkian sentence. So it's a very parallel construction. Okay. Now, I mean, as I said, that already Henkian, but also others complained that, I mean, this provability predicate is actually a very weird one, this one. Yes, it's weird. And people thought, actually, Kreisel's answer is not really interesting because you're using this non-standard provability predicate. But what people didn't criticize was that the way self-reference was achieved, if it is really self-reference, I mean, this was not criticized. And I find that interesting. I mean, the only thing I found was, I mean, Smorinsky kind of said, well, self-reference is a little bit weird here, but it's basically okay. Now, I should say, I mean, in order to get a Henkian sentence that is provable and a Henkian sentence that is refutable, Kreisel employed two different provability predicates. But in fact, that's not really necessary. So you can start with the second provability predicate that is refutable. But if you apply to the second provability predicate, where you have here x different from T2 and so on, but if you applied here the standard diagonal construction, you would in fact not get a refutable, but a provable sentence. This is really an example where you have one predicate, and depending on how you get a self-referential sentences, you get once a provable sentence, and if you diagonalize in another way, I mean, if that's proper self-reference, then you get a refutable sentence. So there's really, this is a straightforward example of this second dimension of intentionality. It does not only depend on how you express provability in the language, it also depends on how you construct your allegedly self-referential sentence. Okay. Okay, yeah, that's what I just said. Should have shown you this earlier. Okay, now here is now an attempt to make, I mean, because in Kreisel's proof, it might be a little bit confusing what's going on here. Take this sentence here in English. So sentence 2 is syntactically identical to itself. So clearly this sentence, or I would say clearly this sentence claims about itself that it's self-identical. I think that's fairly uncontroversial. But does the sentence say about itself that it's identical to 2? Now, this is exactly what's going on in Kreisel's proof here. So you already have your sentence T1 fixed, and then you plug in T1 into this formula. And it's here, I mean, similar. You could say you have as your predicate is identical to sentence 2, and then you could diagonalize in the usual way and say, this sentence I'm uttering right now is identical to sentence 2. That's, of course, a false sentence. The sentence I'm uttering right now is different from this one. But you could also say, in a sense, but this sentence 2 somehow claims that it's identical to sentence 2. And I'm not quite sure, I mean, I lack a little bit intuition. It's not the standard way of self-reference, but Kreisel exploited this fact. And I mean, he would have said, yeah, this is self-reference. I mean, this sentence says about itself that it's identical to sentence 2, and that leads then to this, well, deviant answers to Henkin's problem. So I think this is really the heart of the matter of Kreisel's answer to Henkin's problem. And you can see it's a strange way of getting self-reference. Okay. Now I should continue with the story of Henkin's problem. People insisted, forget about these strange Kreisel provability predicates. They do not really express provability. Let's go for the natural one. Never mind what natural means, but you can simply go to the textbooks on Gödel's incompleteness theorems, and there you will find formulae that express provability in arithmetic. And once you fix this predicate, I mean the natural provability predicate, if you prefer, then the nice thing is, then this intentionality of self-reference disappears completely. So whenever you have a fixed point of this predicate, then it will be provable. And since they're all provable, they're all equivalent. So that's fairly trivial. So if you have a fixed point gamma 1, it's a fixed point of provability, that's a fixed point of provability, then they are both provable and thereby equivalent. This is what Loeb's celebrated theorem tells you. We don't have to go into this. But the nice thing is standard provability predicate means forget about intentionality of self-reference. The nice thing is it's not only for the Henkin problem that the intentionality of self-reference disappears. It's the same for negated provability predicate. So if you have two fixed points of not provable, these are Gödel sentences. If they are fixed points, then they are provably equivalent. intentionality disappears. However, I think that for other predicates different from standard provability, there is a problem of intentionality. And as we have seen, the Kreisel provability predicates are examples where it does matter, but they are not the natural ones. So that's why it's not in conflict with Loeb's theorem. But it seems to me once Loeb had proved, or implicitly proved, that for standard provability, in the way you achieve self-reference doesn't matter, logicians were quite happy. Now we can finally forget about these problems in Kreisel's paper. All the fixed points are equivalent anyway, so this dimension of intentionality, it seems, disappears completely. But I think that's not the end of the story. I mean, one question that still remains open is the following one. I mean, now people very often will tell you what Kreisel proved is if you take a non-standard provability predicate, then you can get a refutable Henkin sentence. That is a sentence that claims about itself that is provable. I mean, that we get provable Henkin sentence follows from Loeb's theorem. If you keep everything canonical, you get a provable sentence. And so to my knowledge, this question hasn't been answered so far. But of course, once Albert got aware of the problem, there's a solution. So by tweaking Kreisel's construction, Albert was able to give a Henkin sentence that is defined via the usual diagonal construction, the Gödel diagonal construction, but of course employs a non-standard provability predicate, and that is refutable. And I mean, just to re-emphasize that, if you have a canonical provability predicate and a non-standard diagonalization, then of course Henkin sentence will always be provable because Loeb's theorem tells you, doesn't matter how you get the fixed point, always provable. So we have there a fairly complete picture, and but the problem is that Loeb's theorem is specific to the canonical provability predicate. But what about other provability notions? We have seen Kreisel's provability predicates are deviant. There it does matter how you get diagonalize. What I would like to ask the audience, what happens if you use, for instance, the Rosser provability predicate, which is very well known in metamathematics. What is known is that the fixed points of the Rosser provability predicate are not equivalent. So, for instance, a tautology, something like naught equals naught, is a fixed point of Rosser provability, but also contradiction such as naught equals 1 is a fixed point of Rosser provability. What happens if you express in a somehow natural way a sentence that claims about itself that it's Rosser provable? Is that sentence provable, refutable? I don't know. We have to wait for Albert. Now, another predicate, and this is actually the predicate I started with, is the partial truth predicate. And I'm now going to talk a little bit about partial truth predicates. First, I need to introduce the notion of a sigma 1 sentence. Details are very tricky, but they don't matter again. Think of sigma 1 sentences as sentences that do not have an unrestricted quantifier except for the first quantifier. So there may be one unrestricted existential quantifier at the beginning, but all the other quantifiers will be restricted. And then there's a formula. There's a formula TR such that you can prove phi is true if and only if phi, but of course only for sentences phi that are sigma 1. Of course, we can't have this for all phi. That would contradict Tarski's theorem on the undefinability of truth, of course. But at least for this class of sentences, we can have a provability predicate. Yeah, and there are such truth predicates. I won't show you how to define them. And what's important is this formula itself can be chosen as a sigma 1 formula, which means this formula here is itself a sigma 1 sentence, so it can be applied to itself. That's of course also the reason why you can't get a liar paradox out of this, because if you negate this sentence, you don't have a sigma 1 sentence anymore, so there's no danger of contradiction. But since this formula can be chosen to be sigma 1, you can construct a truth teller. First, of course, there are many fixed points of this formula. Again, take your usual tautology, naught equals naught, that will be a fixed point. That's the basic thing about the truth predicate, that it has many fixed points, or just fixed points. You can take naught equals 1, that's a refutable fixed point. But I was interested, what do we get if phi somehow claims about itself that it's sigma 1 true, and this is itself a sigma 1 sentence? And the amazing thing is, this is now not talking about some weird truth predicate. This is a truth predicate that is definable in all decent formal theories of syntax. So there's a definitive answer. So what won't count is to say doesn't have a truth value, anything like that, simply because that would mean you would say about a purely arithmetical sentence, it lacks a truth value, which we probably don't want to say. Okay. So this is what I just said. There are these fixed points. One way to go about this is, one sigma 1 truth predicate is actually this predicate provable sigma. So the problem is you want to show phi equivalent to provable sigma phi. And actually, that's already provable in sigma, or one direction is provable in sigma itself. So if phi is sigma 1, then you get phi arrow provable phi by what's called sigma 1 completeness. So that direction is for free. But if you then go in your theory to something stronger than sigma, that has more induction, for instance, then you can actually prove about this weaker system sigma that phi and provability of phi in sigma are equivalent, because you get reflection principles. So in fact, in piano arithmetic, sigma provability is a sigma 1 truth predicate, and its fixed points, so that's not our provability predicate, where all the fixed points are provable, and you can show that via Lüb's theorem. Yeah, so that's how all started. I was wondering, but okay, this answer somehow doesn't count. What about the real truth predicates? Actually now it becomes very awkward, because now I was using such phrases as the natural sigma 1 truth predicates. And natural is defined as, you find it in the standard textbooks of meta-mathematics, so I don't know what that means, natural. But I'm kind of a loss of what makes a good sigma 1 truth predicate. There are different predicates satisfying this condition on the previous slide. And what really became difficult, even if you fix a sigma 1 truth predicate, there are still different ways to achieve self-reference. And what's good self-reference? Naught equals naught is not good. But even when you insist on the Kreisel-Henkin condition, there are different ways to diagonalize. And some of these sentences that say about themselves that they're sigma 1 true are provable, and others are refutable. That's actually an adaptation of Kreisel's technique to the sigma 1 truth predicates. And that really happens for one and the same sigma 1 truth predicate, that certain fixed points, even self-referential fixed points in the sense of Kreisel and Henkin are refutable and others are provable. Okay, what we did then is, of course, there was this attempt to say, okay, let's keep the canonical partial truth predicate, which is difficult to explicate. Let's also keep diagonalization straightforward and canonical. What happens then to the sigma 1 truth teller? So here's Albert's answer. The sigma 1 truth teller is actually refutable. So the truth teller for sigma 1 truth is refutable. Actually, later on, I talked to Van McGee, and it seems he had this result 10 years ago. Okay, so that tells us everything about the sigma 1 truth teller. So for the specialists, they know sigma 1 is just the starting point for a hierarchy. There's also pi 1, and then you can go higher, more quantifiers. It seems the pi 1 truth teller is provable, and beyond that, no idea. And it seems to be difficult. I mean, not because I can't solve it, but because Albert can't solve it. And it seems that the techniques that are used for getting this and to decide the truth teller for pi 1 truth don't apply to these higher truth tellers. So that seems to be difficult. Okay, then what I'm really not happy about is, this here. This became very difficult, tricky, because what you are doing, for provability, you can kind of talk about a natural provability predicate and ask about that. But here it becomes very odd. Sigma 1 truth seems to be something very artificial. What's a canonical sigma 1 truth predicate? And in particular, I was not happy with this talk about this standard diagonal construction. To say that this is the natural diagonal construction is kind of weird, because I guess we think that Gödel's method of constructing a fixed point of not provable was pretty ingenious. That's nothing that's completely direct and natural. Otherwise, it would have been trivial, I guess. So what I would like to ask is, what's a good diagonalization? That would help us also, to narrow down possible answers to such questions as Henkin's problem. Okay, pick a provability predicate. Is the sentence that says about itself that it's provable, or that it's sigma 1 true, or that it's cut-free provable, or and so on? Are these sentences provable, refutable, and so on? And you have to pin down what it means to say about itself to have this property. And I think this is not clear. First, what is clear, that the Kreisel-Henkin condition won't do. We have seen that. There are predicates where you have sentences that say about themselves in the Kreisel-Henkin sentence that they are provable, but they have different properties. And I don't know, that depends on how you think about Kreisel's answer to Henkin. Are these Kreisel self-referential sentences, do they really claim about themselves that they are provable? Or you remember the sentence 2, the sentence 2 that says about itself that it's identical to 2. Does it say so? I don't know. Anyway, what I try to do, this is just, very, very sketchy. It seems to me, in order to say about a sentence, yes, this sentence claims about itself that it's property phi, you need more than just the Kreisel-Henkin condition. So, what Kreisel and Henkin had said, well, it must be of the form phi of p, and then this term t must denote the entire sentence. I think they were on the right track. But what we need is something stronger. And here's one proposal. it fixes the problems I'm aware of, which does not mean it fixes all the problems. So what I achieve, we have a fixed point operator, f, and then the sentence that claims about itself that has the property phi must be of the form f of phi, where f with a dot under it is a representation of the function phi. So phi must be primitive recursive, something like that, then it can be represented, and the self-referential sentence must be of this form. And this, in fact, I mean, so basically what's going on in the formal part must be the same that's really going on in the fixed point operator. This is a condition that is satisfied by the usual Gödel construction. But of course, there are slight variations on Gödel's construction, namely exactly how you plug in a name for a sentence. Of course, you can use the numeral for the Gödel number, but you can also use some other term. That will be okay, but otherwise, it excludes all weird diagonalization. For instance, I mean, it rules out, for instance, Kreisel's very weird diagonalizations. And I think it helps to pin down what it means to say about a sentence, that it ascribes to itself a property phi. Okay, so I'll come to the conclusion. So this is something you should remember for life. Never say something like, this sentence that says about itself that it has a certain property. Maybe you can do so in some cases, like provability, where at least all these sentences will be provably equivalent, but otherwise there is not the sentence that says about itself that it has a certain property. There can be many different sentences that ascribe to themselves a certain property, and they can have completely different properties. So in some cases, as we have seen, it matters which fixed point is used, even for such fairly trivial predicates, such as identity 2T1. Even there we already get weird results. And then, I mean, this is the Henkin-Kreisel condition. I mean, even if we, stipulate that the sentence that says about itself that it has property phi has to be of this form, that is P of T, where T then denotes this sentence again, doesn't guarantee that we have really pinned down the sentence that says about itself that it has property P. And these sentences can have different properties. And it's, this is because of the Heck-Milne discussion. They've even questioned whether this is a necessary condition. But actually, I'm quite happy. I've got so many problems. I'm quite happy to say, yeah, that's a necessary condition. But there may be, we might hope that we could fix the problem and really force proper self-reference by imposing an additional condition, and that was on the previous slide, this uniform fixed points. And I would hope that this would exclude sentences that just happen to be fixed points and that are not really self-referential in a deeper sense. And I can now see that Hannes is getting nervous, so I better stop here and thank you for your attention.